Hello everyone. So today we are going to discuss about stabilization of soil using chemicals and polymers and stabilization of soil by electrolysis. Stabilization of soil using chemicals and polymers and stabilization of soil by electrolysis. Chemical stabilization. So first we'll see what is the chemicals that are using for stabilizing the soil. The chemicals stabilizations are stabilized by adding different chemicals. So the soils have been treated by different chemicals. Thus, its main advantage is that the setting and the curing time can be controlled. The following chemicals have been successfully used, that is calcium chloride, sodium silicate, polymers, chrome lignin, and other chemicals. So all these are the chemicals that are using for treating the soil, that is calcium chloride, sodium silicate, polymers, and chrome lignin, and other chemicals. So hope it is clear. Now the next topic is, under this technology, soil stabilization depends mainly on chemical reactions between the stabilizers and soil minerals to achieve the desired effect. So that is the when we add chemicals to the soils, the chemicals will react with the soil minerals to achieve the desired effect. The different techniques of soil stabilization is soil lime mixture, soil cement mixture, that we have explained in the last class, how we can mix soil with lime and soil with cement, etc. And today we'll discuss about how the chloride or sodium chloride, etc., reacts with the soil and to get stabilized. Calcium and sodium chloride is the chemical that we are using to react with the soil so that we get a desired or required stabilized soil. So first is, both calcium and sodium are soil stabilizers available as byproducts from sodium carbonate or from other chemical process, can also be obtained by reacting lime or limestone with HCl. So these are the process by which we'll get this calcium and sodium chlorides, available under the trade name Paste Wet as 29% solution, which is a byproduct in the manufacture of fluorocarbons. So all these are the methods by which we'll get this calcium and sodium chlorides, and these are the chemicals that we can use for stabilizing the soil. And what are the effects of these chemicals on the soil? That is, it creates a colloidal reactions, altering the characteristics of pore water that is present inside the voids of the soil. They are hygroscopic and lower the vapor pressure of water. These changes mainly reduces the escape of moisture from the soil. Frost heave in soil is reduced as the salt reduces the freezing point. All the benefit of the salt are due to its presence in the soil for water. So what are the effects? So let's explain in detail. First, this reaction is a colloidal reaction. They are hygroscopic and lower the vapor pressure of the water inside the voids of the soil particle. So water will be present inside the pores of the soil particle. So when we add chemicals to the soil, it will alter the chemical or it alter the property of the soil inside the voids, and thereby we can get a better soil. These changes mainly reduces the moisture inside the soil. The frost heave in soil is reduced. That is, the freezing of the water inside the voids will get reduced. And all the benefit of the salt are due to the presence in the soil or water. Now next is sodium silicate. Sodium silicate is the another chemical that we are using. It is used as solution in water known as water glass. So the other name of sodium silicate is water glass. It is directly injected into the soil. It increases the strength of the soil and makes it impervious. So the permeability of the soil. What is permeability or impervious means? The ability of the soil particles to transmit water is called permeability. So it that property of the soil can be altered by adding the sodium silicate to the soil. That is, it becomes impervious. That is, it resists the movement of water through it. It acts as a dispersing agent. It increases the maximum compacted unit weight of the soil. So it increases the density of the soil also. And the chemical required varies between zero point 0.1 to 0.2 percentage of the weight of the soil. The method is relatively inexpensive, but long-term stability is doubtful. So by adding the sodium silicate, we can stabilize the soil, but for a shorter duration of time. Long-term stability cannot be expected from these kind of treatment. The treated soil may lose strength when exposed to air or groundwater. So what are the so this is the second chemical that we are adding to the soil to alter the property of the soil. Now next is lignin and waterproofers. Lignin is an admixture that we are adding to the soil. Lignin is a water soluble additive available in powder form and also in the form of sulfide liquid. As lignin water soluble, a chrome lignin was developed to make stabilization effect more effective. Lignin also reduces frost heave in soil. So all these chemicals are altering the freezing point of the water inside the pores of the soil. That is, in the colder region, what happened is the water inside the pore become frozen or ice. So ice will be formed inside the void, so that the volume of this will expand and the cracks will be formed. So such problem can be minimized by adding those chemicals to the soil. So that is the another chemical that we are adding, that is lignin. Then next is waterproofers. These chemical prevent or reduce the attack of water on the soil. One end of the waterproofer molecule remain absorbed to the soil and react with it. Other end being hygroscopic repels water and makes the soil mineral waterproof. So the next waterproofers, as the name indicate, it makes the soil repel to the water. That is, when you pour water to the soil, inside the voids of this soil, this waterproofers will be present. Thereby it repels the water out and thereby reduces the permeability. One end of the waterproofer molecules remain absorbed, so that when we add this chemical, that is waterproofers, to the soil, what happens? It gets absorbed by the soil. So when you add waterproofers to the soil, it gets absorbed and repels the water out. Waterproofers recognized as soil stabilizers are, examples of waterproofers are alkyl chlorosilane, siliconates, amines, ammonium salt, etc. They do not increase the strength but helps the soil to retain natural strength in the presence of water. So even if it is a highly rainy condition or having underwater, if we add this waterproofers to the soil, what happen? It will reflect the water out and thereby stabilizes the soil. So that is the condition when you add waterproofers. So what are the chemicals that we are adding? Calcium and sodium chloride, sodium silicate, lignin, and waterproofers are the chemicals that can be added to the soil to alter the properties. Then next is polymers. Polymers are long chain molecules formed by polymerizing of certain organic chemicals called monomers. They may be natural or synthetics. Resins are natural polymers and calcium arsenate is synthetic. When added to the soil, reaction takes place. Polymers are long chain molecules formed by polymerization. So when you add the polymers to the soil, two ways of reaction takes place. The way of incorporation or reactions are a monomer along with a crystalline is added to the soil to polymerize and react with the soil, or a polymer is added to the soil in solid or solution form. So along with the catalyst we can add, or we can directly add as a solution. So these are the two ways by which we can add this polymers to the soil. So it is another kind of chemical that we can add to the soil to alter the property. Then other chemicals that we have explained, waterproofers such as alkyl chlorosilane, siliconates, amines, ammonium salt have been used for soil waterproofing. Then coagulating chemicals such as calcium chloride, ferric chloride have been used to increase the electrical attraction and to form foliated structure in order to improve the permeability of the soil. Then dispersants such as sodium hexametaphorate are used to increase the electric repulsion and to cause dispersed structure. The compacted density of the soil is increased. Then phosphoric acid, it's combined with a wetting agent for cohesive soil. It reacts with the clay minerals and form an insoluble aluminum phosphate. So these are the chemicals that we can add to the soil to alter the property. So I will explain it once more. What are the chemicals that we can add? That is calcium chloride, sodium silicate, polymers, and other chemicals. So calcium chloride, where we have explained, sodium silicate, lignin, waterproofers, and polymers. Then, for example of chemicals that we can add is this is how we can pump the chemicals to the soil. A truck applies chemical stabilizers to reduce the soil erosion where vegetation cannot be used. So a nature-friendly method to reduce the erosion is by planting vegetation. But in some cases, it's not practical to plant trees or vegetation on the slope. In that area, we can apply chemicals so that the erosion can be reduced. Then application of chemical additives in soil stabilization. So a lime or any methods can lime. This is a lime that is being applied to a soil layer. So to stabilize it. Then this is before stabilization and after stabilization. Before stabilization, see the nature of the soil here. It is full of water or wet solute or and here we can see that this is stable form. Stabilization. So next topic is stabilization of soil by electrolysis. So this is the method that is a newly applied method. On one of the most common cause of foundation movement is volume change of active clays in response to environmental and vegetation, notably clay shrinkage in long dry spell, and clay swelling involves the removal of large trees and heads. So this is the condition in which we can use this electrolysis, that is the high expansion and contraction or shrinkage of clay. So in the case of clay, the volume changes drastic. There is a drastic change of volume change. When you apply water to the clay, it will expand or it will change its characteristics. Okay, so electrolysis is a method that we can apply over clay. Electrolyte stabilization or electrolysis is a technique of applying an electrical current through the soil mass to promote the migration of chemicals from injection points, which are usually the electrode themselves. So when you apply chemicals and all, the electrolysis can also be applied through the soil mass. So the electric current is passed through the soil mass. So thereby the water present inside the voids will react it with or splits into hydrogen and OH negative. So that is how the reaction takes place when you apply current through the soil mass. This technique is this technique is particularly suited to weak clayey soils that requires strengthening and yet possess a low hydraulic conductivity, thus preventing the economic introduction of chemical grout using conventional hydraulic means. So the grouting is mainly done by pumping water and all, but the clay soil or clayey soil is having less hydraulic conductivity, like less permeable, so the water cannot move easily through the clay. In that situation, we can use this electrolysis method. We can pass current through the soil mass, thereby we can have a movement of water through it. So let's see how we can apply this. Electroosmosis is the method when an electrical potential difference is applied across a soil mass. That is, when we apply an electric current through the soil mass, cations and anions are attracted to the cathodes and anodes. So we are inserting a cathode property and an anode property inside the soil, like two rod will be there. One will be cathode and another will be anode, and the electric current passes in between these two, and what happened is the water inside the voids will split. This forced migration occurs most readily by the ions with the greatest mobility. So ions will be formed like H positive and OH negative, and it will have a tendency to attract. So cations will be moved towards anode and anions will be moved towards cathode. Within a soil mass, these ions are to be found in pore water existing between the soil particles. The movement of the ions with the pore water causes a transfer of momentum to the pore water. So that movement of ions causes the pore water along with it to move. The corresponding direction and rate of pore water movement are determined by the net transfer of momentum by both cations and anions. So this pore water ions, that is OH negative and H positive, will be moving towards cations and anions that we have inserted. Because of the nature of clay formation, which usually result in significantly negatively charged clay particle, the predominant ions within the pore fluids are cationic, and water therefore moves from anode to the cathode. So the water will be moving towards cathode. The two fundamental factors that control the degree of water migration are the cations, anion distribution within the pore water and the water cation distribution within the soil. So I'll explain it so that it will be more clear for you. So these are the two roads that we are inserting. First will be an anode road and second will be a cathode road. And see how the electric charge will move in between this, and the water or the pore water inside the soil mass will split into H positive and OH negative, and H positive will move towards cathode and OH negative will move towards anode. The cathode is a well. So here this OH negative is a well point which collects the water. So H positive along with some water will be moving towards this cathode, and it is represented as it will be an open well. So water that is reaching this well can be directly pumped out. The cathode is a well point which collects the water, have to drain from the soil and discharge the water as in a conventional well point system. So this is anode, and here you can see this is the slope of the soil mass. In between there will be a road or something. So this is the slope, and at the slope this anode will be installed, and away from the slope this cathode will be installed. And the water normally, the water will be having a tendency to move towards this direction, but when you apply current in between these slope, the water will start moving towards cathode in the opposite direction. When an external electromotive force is applied across a solid liquid interface, that layer is electros. The process is called osmosis. As the surface of fine-grained soil particles causes negative charge, the positive ions in solution are attracted towards the soil particles and concentrate near the surface. The positive ions adjacent to the soils, that is H positive ions, adjacent to the soil particles, and the water molecules attached to the ions are attracted to the cathode and are repelled by the anode. So this ions, that is positive, H positive ions along with this water molecules will be moving towards cathode. The free water in the interior of the void space is carried along to the cathode by this viscous flow. By making the cathode a well, water can be collected in the well and then pumped out. Sheet piles can be used as electrodes. Anode for normal applications are old pipes. So anode that we are using is old pipes of 25 mm to 50 mm diameter. They can be placed singly or groups of 2 or 3. Spacing between them should not be closer than 0.7 meter. The cathode well should extend from the surface to the bottom so as to allow water to discharge into them. So this is the figure that is the splitting of water ions as H. That is, this is the cation well. That we are drilling. This is the open well, and towards this the water molecules will be attracted. That is H2O will be attracted, and this is anion. This is the soil particles that have a negative charge in them, and this H positive will be attracting the soil particle, and this will be moving towards this cathode. So in this figure, you can see that this is the slope, and near to the slope we are installing anode, and this is the cathode well in which we can collect water. And this is the way in which the water will flow now towards the cathode. That is, the water that is present inside the voids of the soil particle will be moving towards this cathode. So see, the direction of flow is towards the cathode. When an electric field is applied to the fluid, usually electrode places in inlet and outlet, the net charge in the electrical double layer is induced to move by the resulting Coulomb's force. The resulting flow is termed as electroosmotic flow. The use of electroosmosis for treatment of soft clay is a common ground improvement technique. So electrolysis method is mainly used for in clay. A number of chemical, physical, and mechanical interaction occurs during the improvement of soil by this technique. Mechanism. Cations are formed in pore water when the dissolved minerals go into solutions. These cations move towards a negatively charged surface of clay minerals to satisfy the electrical charge. As the water molecules act as dipoles, the cations also attract the negative end of the dipole. When the cations move to the cathode, they take with them the attached water molecules also. That is, H positive will take the water molecules along with them towards the cathode well. Installation of system. Anodes are in the form of steel rods located near to the toe of the slope of the excavation. So when you have a slope like this, in, at the near to the slope, you can place this anode. Cathodes are in the form of perforated pipes, that is open pipe, or the pipe which is permeable, that is resembling a well point, installed in the soil mass about 4 to 5 meters away from the slope of cut. The electrodes are so arranged that the natural direction of flow of water is reversed. So I have explained that normally the water has a tendency to move toward in the direction of slope, but when you install this system, the water will be flowing in the opposite direction. This arrangement is required to prevent slowing of the slope. So what do you mean by slowing? Slowing is wetting of the downstream side. That is, when the water flows in this direction, this is the this end of the slope will be wetted gradually, and what happened is this entire slope will settles down. So that process is called slowing. So when you reverse the flow of water away from the slope, what happens? The slowing also reduces, and thereby the stability of the slope can be improved. Then system requirement. The system requires about 20 to 30 amperes of electricity per well at a voltage of 40 to 180 watts. The consumption of energy is between zero point 0.5 to 10 kilowatts per m cube of soil drained. So for a one volume, we need 1 m cube of volume, we need about 0.5 to 10 kilowatts of electricity, so that this process will take place. Then what are the limitations of electroosmosis? This process requires stabilized and sophisticated equipment as well as electrical consumption of high amount in associated with this process. Thus, it is highly expensive drainage process compared with the other method. So, when you compare with chemical stabilization or mechanical stabilization or physical stabilization, this electroosmosis is much more expensive based on the electricity that is required for this process, or anodes and cathodes installation. All these are the initial cost that is required. So this is bit more expensive compared to any other method of soil stabilization. Then suitability. This method should be used only in exception cases when other methods cannot be used. It is normally used to drain water in a cohesive soil of low permeability. So to increase the permeability of a particular soil, we can use this method. Electroosmosis. So when you install a cathode to near to the slope and anode at the end of the slope, the water will have a tendency to flow towards this cathode. And when we have to apply a current, okay, where the current passage of electricity should be there, a DC power should be connected, and the water will split to like H positive and OH negative, and the cations and anions will be flowing towards your cathode and anode. So this is the figure shows the clay particles having water molecules around it. The parallel arrangement of clay particles with hydrated water layers, its face-to-face attractions by thin water layer, which allows attractive force to dominate, and thus the water along the soil particles will get attracted towards cathode. What are the applications of electroosmosis? The main application of electroosmosis is the strengthening of slopes and cutting. Electrokinetic consolidation. So for consolidation also we can use this electrolysis method. Dewatering of sewage sludge, dewatering and recovery of water from mine tailings. Thank you. Then we'll have a revision for that electrolysis or from beginning. So we were explaining about soil stabilization by chemical methods and by electrolysis. So in chemical stabilization, the following are the chemicals that we can use for stabilizing the soil. First is calcium chloride, second is sodium chlorides, then sodium silicate, polymers, chrome lignin, and other chemicals. Calcium and sodium chlorides are the stabilizers, like it is in the form of solutions, and it is a byproduct of any other chemical process. This will have a colloidal reaction with the soil particles, altering the characteristic of pore water. It will alter the freezing point of the water that is present inside the voids and reduces the permeability also. And sodium silicate, it is used as a solution in water as a water glass also. It is directly injected into the soil. It increases the strength of the soil and makes it impervious. It increases the maximum compacted or density of the soil. The chemical required varies between 0.1 to 0.2%. Then chemical admixtures. Again, the chemical that we are adding is lignin and waterproofers. Lignin is another solution. Was developed to make a stabilizing effect more effective. Lignin also reduces the frost heave in soil. Then waterproofers are, as the name indicates, it will repel the water out from the voids of the soil, thereby reduces the permeability of the soil particles. Then polymers. Polymers are long chain molecules formed by polymerizing of certain organic chemicals called monomers. So along with this polymers, we can directly add polymers to the soil, or we can add catalysts along with it to activate the reaction. And other chemicals are photophonic acids, coagulating chemicals, dispersant, etc. So this is the way in which we are applying chemicals to the soil. That is a figure showing how we can pump the chemicals to the slope using truck. And thus the effect that we are getting after chemical stabilization of soil. Then electrolysis is a method in which we are passing electricity in between the soil mass using cathode and anode, in which what happens, the water will split into anions and cations and get attracted to it. This method is mainly used in clay, where permeability is much less. Then electroosmosis is the process in which we are inserting a cathode and anode whereas neutral particles are attracted to neither. These forced migration occurs most readily by the ions with the greatest mobility. The corresponding direction and rate of pore-water movement are determined by net transfer of momentum by both cations and anions. So the speed of the movement depends upon the cations and anions movements. So this is the process anode and cathode that has been installed in soil mass, and we are passing electricity through it. So what happened is the water when we pass electricity through the soil mass, the water that is present inside the pores of the soil particles will split itself to OH negative and H positive, and OH negative will be attracted towards anode, whereas H positive will be attracted towards cathode. When an external electromotive force is applied across a solid liquid interface, the layer is displayed with an electroosmosis. So that soil mass will be under electroosmosis action. As the surface of the fine grained particles causes negative charge, the H positive ions are attracted towards the soil particles and concentrate near the surface. The positive ions adjacent to the soil particles, that is water molecules, attached toward attracted towards the OH negative, and that will pass towards the cathode well. So cathode is an open well and anode is a pipe. When the water molecules get attracted towards the cathode, we can easily collect water inside the cathode well, and we can pump out. Sheet piles are sheet piles can be used as electrodes. Anodes for normal applications are all pipes of 25 mm or 50 mm diameter. They can be placed slightly or group of 2 or 3. Spacing between them should be closer than 0.7 meter. So this is anion and cation soil particle. Here you can see when cations are moving towards this cathode, what happen? It will attract the the water particles along with it towards the cathode. And anions will be attracting this cation will attract the water particles along with that is H2O towards the cathode. So this is how we can install this. This is cathode and this is anode. You can see cathode is being installed far away from the slope, whereas anode is installed closer to the slope. So here see what happened. The water has a tendency to move towards the cathode. That is, it is reversing the natural movement of water. Normally, the water will have a tendency to flow like this in towards the slope. But when you install the electricity, we are reversing the flow of water. So when you reverse the flow of water, what happens? The water that is flowing, it is a process in which the downstream gets wet. So that process will be reduced. We are having an opposite flow of water. Cations are formed in pore water when the dissolved minerals go into solution. These cations move towards the negatively charged surface of clay minerals to satisfy the electrical charge. As